Okay, very good. All right, so the other takeaway is this. So I'm gonna talk about actually a lot of quark sector, as you can see the title, Cabibbo-angle. So quark sector, and then, but also I talk about neutrino sector as well. So, and then, so one of the takeaway is that quark sector is pretty well measured for various reasons. You produce a lot of mesons in the lab and so on. You can detect much better, easier than neutrinos. So some measurements, like in terms of parameter extraction, it can be like as good as 10 to the minus 3 or 10 to the minus 4. So in terms of parameter extraction, right? So neutrino, like a neutrino is already BSM, like we have a conversation over lunch. But let's say like in terms of measurement of the PMNS matrix, it can be like as good as like a 10% or maybe a few percent. So what I'm trying to say is that if some deviation in the neutrino sector at the level of like 10 to the minus 3, so this one is not good, 10 to the minus 3, which is not seen in the current at this moment, at least. It's not seen in the neutrino measurement, but could be seen in the quark sector measurement. And this is one example I take is a Cabibbo-angle because this is one of the uh, best measurement in the quark sector. And then why this kind of thing is possible is very easy. So most of the quark good measurement is done by meson decays. So kaon, pion, and also sometimes hyperon, and also like a proton and neutron is also matters. But okay, meson decays are quite important, and also that some it's not really a meson, but like a neutron or the nuclear, right? And then good measurement happens in the flavor changing process. So flavor changing process, and then in the quark sector, always a charge current, right? So you have some quark, UND, and then you have an index of the generation, and then charge current is, so you have a W boson, right? And then, so this side is always something involving like a meson, like kaons and pions, or sometimes hadron, right? Like sometimes baryon. The other side, the good measurement is done by the leptonic decay. So it's already charged current, so you have a charged lepton because you can detect a muon and electron much better than the hadronic final state. Then the other side is always neutrino. So all the good measurement in the quark sector, like a meson decays and so on, always involve the neutrinos. So that's why I say that if something is modified in neutrino sector, could be seen as a quark sector anomaly, and one of which is the Cabibbo-angle anomaly. And this is actually can be generalized beyond the Cabibbo-angle, but this is one of the takeaway. All right, so in my talk, it's very, very simple because it's a blackboard talk. Can you see it? Actually, let me see. All right, so I'm going to talk about what the Cabibbo-angle anomaly, and I'm going to mention the measurement because measurement's really crucial. How it's measured, how parameters are extracted are very important. So measurement I'm going to talk about, and then just introduce a simple sterile neutrino, explain how the anomaly is resolved. One interesting thing is that actually particular mass is indicated from the data. So this is one thing you can see, I hope, in my talk. All right, so what is a Cabibbo-angle anomaly? So first, let me actually go back to the just standard model thing. So we have a VCKM, right? And then you have BU D, and then BU S, and BU B, and then this is like a generation of the charm and top, and you have 4 other elements. And then you know that the VCKM in the standard model is a unitary, right? So I'm going to use just a V. So V dagger B or VV dagger is a 3 by 3 identity matrix, right? And the famous unitarity test is done by off-diagonal component of the, so I think like a bottom and down, so or 3, 1 component. So unitarity predicted this off-diagonal is always 0, right? Which is actually experimentally confirmed. So up to the uncertainty, right? So this is confirmed. And if I remember right, this is like confirmed at the level of the 1%. There are many measurements involved. And then I think this is confirmed at the 1% level. But actually like a most precisely measured quantity in this equation is this one. So VV dagger of the first component, diagonal component of UU, which is VUD square plus VUS square and VUV square. And this is because it's diagonal. In the standard model, it should be 1, right? And of course, other diagonal component is much, much harder because it involves charm and top, right? And then it's actually essentially the relation for the Cabibbo angle because experimental uncertainty, so you have a measurement of the 3 parameters, right? Experiments measure the first 2 quantity very well, but still it's not as good as small as this element. So actually the experimental uncertainty of the VUD or VUS is much actually larger than VUV itself, which is about 10 to the minus 5. And this is a precision of like a order of 10 to the minus 4. So you can actually safely drop this term. And so this is like a sum 2 quantity relation up to the experimental uncertainty. And this is nothing but like a Cabibbo angle, right? So cosine theta c square plus sine square theta c should be equal to 1 up to the experimental uncertainty. So that's why it's actually essentially Cabibbo angle. And then this is parameterized by, this quantity is parameterized by 1 because it should be a 1 plus some deviation. Delta CKM is often people use. I don't think this is a good notation because it's not really CKM. It's really up component, but let me use this notation. And then there is a deficit. So it's less than 1. In other words, cosine square plus sine square is less than 1. So that's the observation. So that's what the current data, and then this is at depends on how you combine the, yes. Yeah, so the question was like what kind of measurements are involved. I'm going to talk about that. So one subtlety is how you actually treat the neutron data set. And it depends on that, but it's actually like a order of like a 3 sigma. So because the neutron data set is at this moment is not a leading measurement. So the nuclear beta decay is one which determines a BUD. So it's about like a 2.8 to 3.8, depends on what measurement you take. So I would say 2.8 to 3.8 sigma. Is that the answer to your question, or? Yeah, okay, so I'm gonna mention, so in the end, I combine everything, but I'm only mention some of leading example in the talk because of the time, right? Yeah, but we included most measurements. Any other questions? Yeah, it's a BU, this one. Yeah, it's about 10 to the minus 5. Square is a 10 to the minus. Sorry, what was the question? 1 times 10 to the minus 5? What do you mean? No. No, BUB is the first generation, the third generation is tiny, tiny. Ah, okay. So I'm saying 10 to the minus 5. Yeah, but okay. 1 point something, 1 point something. So I don't remember the number on top of my head. Hmm? Okay, I cannot answer that digit, but I just checked like it's about 1. If you round the second digit, 1 times 10 to the minus 5, which is enough to ignore for this purpose, right? Yeah. But if you want really precise number, just open PDG. But okay, I cannot do it now. So 3, 5 square, right? So square is this. So it's 1 times 10 to the minus 5, right? Yeah, so I'm correct. So okay, if you to make it, no, no. So maybe 0.98 times 10 to the minus 5. Okay, I think. All right, any other questions? Fine, okay. But thank you for asking the question anyway. So the deficit is this, and then, okay, let me mention the measurements, because measurement really matters. And so the measurement is actually, I want to plot as a function of the neutrino energy, because that really matters to discuss a solution of the sterile neutrino. Okay, so let me focus on the VUD first. So this is 10 MeV, 100 MeV. Okay, so the goal of the measurement is there are two parameters, but actually there are three different ways to measure. So one is VUD, which is usually very well measured, and VUS, magnitude, or the ratio. So you can actually measure three different, and then if you measure two of them, you can test this equation, right? So usually you can combine this or this, but in the global fit, I include everything, okay? But just to simplify the story, right? So the neutrino energy is what really mean is a maximum of the neutrino energy from the point of view of the decay. So first, like there is a 0.7 MeV, which is a neutron decay. So this is a 0.7. And then there is a bunch of the nuclear beta decay. So there are a bunch of range. So this is a 0 plus to 0 plus super allowed beta decay, which is a kind of nuclear physicist way to say that pure vector current beta decay in my, in my understanding. So this is involving like a bunch of like electron neutrino, right? And then, so there are 20-ish measurements, and most important one, so actually one particular transition really dominate the precision, which is like a 28 of aluminum going to 28 to um, magnesium. And then, okay, so let me just focus on this particular one. So in that case, it's a 3.2 MeV. So neutrino energy maximum is 3.2 MeV. Okay, then, so this is for the measurement of the VUD. So this is like the first two up and down quark are involved, right? So if you care about the VUS, you have to deal with a kaon, right? So for example, since we have to talk about kaon, it's about 100 MeV-ish. So for example, K2 pi L nu. So L can be muon or electron. So this is to measure VUS. So magnitude of the VUS can be measured from this, not the ratio. Or if you combine like the ratio of the K2 pi, sorry, not pi, K2 mu nu divided by pi 2 mu nu, this gives you the ratio as observable, VUS and VUD. Okay, and then there are other things which I completely ignore. It's in the GeV range. So tau decay. But for the purpose of my talk, actually, tau is not very important. So I include the tau data, but to make a point, it's not necessary. So I will just omit that. But there is tau to k nu or tau to pi nu. That kind of things is exists to measure this kind of quantity. All right. So observation is like this, and also like this, and this to measure this. And then just to remind you the value, okay? So there is a unitarity relation. So there is it's smaller than 1. So there are two possible ways, right? Anomaly, either greater than 1 or smaller than 1. So in this case, it's deficit. So delta is smaller than 1. So delta is negative, right? So, okay, so if you want to explain this situation, you somehow want observational VUD or VUS is maybe smaller than actual VUD or VUS, because I don't try to mess up the Cork sector. So this guy is a true VUD, which VUD VUS, which follow the unitarity, but somehow observation is messed up, and then the observed quantity might be smaller than the real values. Okay, so this is the direction I'm trying to go. All right, so I'm trying to get this situation by introducing sterile neutrino. And the reason is very obvious. Yeah, yes, please. Sorry, can you say it again? Uh, yes, decay constant is the theory calculation. Yes. I think mostly the lattice, but okay, so.
Perturbation theory.
Okay, I don't remember that this particular
also k pi L nu, there are two form factors. There is F plus, F minus.
Yes.
So, I mean, one has to use those.
Yes. So
from somewhere.
Yes. So people did calculate this form factor and also the decay constant as well, which I didn't do, but I just use the extracted result of the VUD and PUS.
Okay.
Yeah.
Thank you.
So I'm sure that they are more expert on this kind of topic, but yes, at this point, like I'm trying to trust this calculation and then take the error bar they provided and then try to interpret for the new physics. Yeah, of course, like one thing I'm not sure is about the actually VUD part, not VUS part, because it's a beta decay really dominates, and it's a looks like a really difficult to calculate, especially the error bar changes over years. So especially after people notice there is a unitarity violation like this one. So, but like I don't have enough expertise to comment on this. But this is maybe something people can improve. All right, so sterile neutrino is very simplest one I introduced. So let me say that this is a standard model. The neutrino, and then just I try to use to be simple by two parameters, which is a mass of the sterile neutrino and the mixing angle. So let's say this is standard model like left-handed neutrino is expanded by cosine theta L, and then this is like a so-called active one, and then sine theta L, and then sterile. And then in literature, I can relate this theta L to be approximately this L4 in the neutrino community notation. I just use the angle theta just to, and then if you want before diagonalize, I have a cosine theta of L nu 4 minus sine theta L, and then nu L prime. So L is index of flavor. Okay, and then let me just focus on this one. Okay, so then what's really important is okay, so we have a charged current, right? So charged current, W. So originally I have just G and then nu L and L, right? But if it has to be expanded by the nu L prime, which is active neutrino and the sterile neutrino, this vertex is shared by two particles, right? So L is the same, and then L prime G times cosine theta L plus I have this G times sine theta L and then stereo, right? So maybe this kind of things, okay, so observed quantity is lower than VUD may be achieved because coupling reduction is always necessary to happen here, right? So, but actually it doesn't work as naively thinking. So I will show you how. But anyway, important thing is that this weak interaction is split to the active and then stereo one. And then the coupling is leaked to the sterile neutrino by the small mixing angle. Okay, so then guess I think I still have a time. So let me take two limits. Actually, the one limit is maybe enough to uh, explain. Okay, so let me actually raise this side. Yeah, are you asking about this one? Okay. Yes. So because I don't care about these small neutrino masses. So I actually this is a if you want the mass eigenstate, this is sum of the three active neutrinos. Does it make sense? Yeah. But like, as long as I can ignore the neutrino, so-called neutrino masses, this is a good approximation, right? Because I can completely drop the neutrino mass because the measurement energy scale is MeV, right? And then this is like a milli electron volt or so this is completely dropped. Or maybe I can say that you can get the correction of like the solar neutrino mass divided by like MeV or something, uh, if you want to be precise. But we don't have that precision. Okay, so the solution. So let me try the one simple case, the very heavy stereo neutrino. So okay, because naively speaking, I don't need this diagram because I want a coupling reduction, right? So okay, I have a cosine theta, so I just remove this diagram, making this new L, a new for heavy. But actually, it doesn't work, and actually, it goes completely opposite direction because of the G Fermi. So so you have to be careful about how the observation is modified. So you have to be careful. G Fermi is also modified. Because any process involving neutrino is affected. So G Fermi is basically measured by muon decay. Right? So muon decay, and then I have a W here, and then U mu, okay? Then actually prime, and then E and E. All right. So usually we just say, okay, so there is no W and then G Fermi is there. But in this particular case, I only have this size of the vertex. So each vertex has a coupling reduction. So cosine theta mu is here, and then cosine theta E. So observed G Fermi should be a combination of, I lost a good chalk. Okay, good chalk is this one. So G Fermi observed is a combination of the true G Fermi, like a VEV, times the cosine theta of the mu and cosine theta of E. Okay, so we actually don't know the value of the G Fermi because as long as you use the muon measurement, muon decay, you only measure the combination, right? Then by using this G Fermi observed, let's look at the beta decay. So UD, and then you have a W. So no new physics is here, but you have a W here, and then let's say electron and then muon, electron type neutrino. Just want to make sure that I put the prime here. So I don't have a diagram of nu4 because it's heavy. Okay, so in this case, the observation is that you have to use a G Fermi observed times BUD observed because you always have a G Fermi when you measure the off-diagonal mixing angle. So then this is given by actual G Fermi times mixing angle here, cosine theta E. So BUD, sorry, I have to put the BUD here. So BUD and then cosine theta E, right? So now I plug in this expression to here and then take a ratio. What happens is that BUD observed is given by cosine theta E, cosine theta E, cosine theta mu times BUD. So partial cancellation is observed here, but you don't cancel this one, right? So, which is completely opposite to what I want, right? Naively, I have a coupling reduction. If you look at just this vertex, there is a cosine theta indeed, but also G Fermi is messed up, like this one. So you have to have this 1 over cosine theta, which is apparently greater than 1. So this is greater than EUD. And then if you look at the other observable, so VUS depends on the observable you take, but it's either VUS divided by cosine theta of E or mu. Ratio actually doesn't change. Observed is actually doesn't change. So this is doesn't change, but this one and this one has a 1 over cosine theta. So in the end, when you test this 1 plus delta CKM parameter, right? So let me say I look at this VUD square and the cosine square theta plus BUS square, and then this actually depends on what measurement you take. And this is actually always greater than 1. So this is actually opposite to what I want. Like the anomaly suggests this is negative. Data suggests it's negative. But actually heavy sterile neutrino doesn't work. Okay. And how about the very light sterile neutrino, right? So very light sterile neutrino, in this case, you have all kinds of diagrams. So you have mu4, mu4, or like a combination of the nu4 and nu e, or nu mu, nu4, or nu4, nu4. And then if you sum over, you just come back to the standard model because you don't detect a sterile neutrino in the final state. So mathematically, what you see is that something like this. G Fermi observed is G Fermi times cosine square plus sine square of the E and E times cosine square theta mu plus sine square theta mu. So this is just one, right? So you have a 4 diagram. This, 2, 3, and 4. So and then if you sum over, just get the G Fermi. So very heavy sterile neutrino doesn't work. Actually, it's make it situation worse. Very light one doesn't do anything. Okay. So what is the solution? The solution is very simple. What really happened was actually because of G Fermi, right? So G Fermi was modified. That's why you have a cosine theta in the denominator. So in order to avoid that issue, prescription is that you can put the sterile neutrino around this mass scale. So what happens is that if the sterile neutrino is, let's say, like a 10 MeV, which is heavy enough for the measurement of the beta decay or neutron decay, so you don't have a diagram involving the sterile neutrino, but 10 MeV is light enough for the energy scale of the muon, so the muon decay is not messed up. So although muon decay is very precisely measured, this 10 MeV sterile neutrino and then doesn't really affect even that the G Fermi measurement is extremely precise. So in that case, the G Fermi is same as a true one. Then you don't have this denominator, right? You only have this cosine theta. So now BUD observed is smaller than actual VUD. So the unitarity relation, observed unitarity relation, is now very simple. So you have 1 plus delta CKM, which is a combination of the observed BUD square plus BUS observed square. And then these like all the measurement, G Fermi measurement or BUS measurement or BUD measurement, these are all standard model like. So what I mean is this is BUS is same as just true BUS square. And the BUD observed is that cosine theta square E and BUD square plus BUS square. And then truth level, there is a unitarity. So BUD square plus BUS square should be equal to 1. And then if I expand this relationship, this is 1 minus sine square theta E times BUD square. Okay, so now actually what the sign is working right. So sine square is obviously a positive number, and BUD square is almost 1, like a 0.99. I don't remember the number, it's almost 1. And then it's a 1 minus. So this is actually agree with the experimental constraint on the or direction of the anomaly, which is a delta CKM is like a minus 1.5 times, okay, let me say, plus minus 0.5 times 10 to the minus 3. So the size of the anomaly actually goes into the mixing angle, right? So the mixing angle, the preferred mixing angle, theta E square, is basically delta CKM, which is like a 10 to the minus 3. So to explain this Cabibbo-angle anomaly, you need a mixing angle square of the 10 to the minus 3, which is very different from the size of the reactor neutrino anomaly, and also the mass scale is very different because I have a sterile neutrino in the MeV scale, actually a few MeV. So this is much heavier than the typical reactor neutrino that people consider, sterile neutrino people consider. And also the value of the mixing angle is extremely, like much smaller than the reactor neutrino case. So this is basically that the conclusion I get from this kind of exercise. Too heavy doesn't work. Too light is same as standard model, but there is a one sweet spot where that anomaly is explained with the right sign. Okay. How much time do I have? So 36 minutes, 2 minutes, yeah. So then let me just draw the global field. So I'm not, let me actually erase maybe that one because that is very basic. So let me just show you that this scenario, of course, as in many other scenarios, have a constraint. So I just briefly mentioned. If you're interested, I can mention in the Q&A. But let me show you that what kind of fit is obtained. So, so this is a mixing angle of the theta e square, and then m nu 4. So I need to look at figure to better illustration. All right. So there is one important mass scale which is about this aluminum transition. So this is around the 3 MeV. Okay. So this is a linear scale and a log scale. So let me draw. This is 10 to the minus 2, 10 to the minus 3, 10 to the minus 4, and the 3 MeV, and then let's say 1 MeV, and then let's say like a 5 or 10. Doesn't really matter, but okay. So like I show here, the mixing angle favored region is 10 to the minus 3. But if it's actually lighter than 3 MeV, it actually doesn't work. So, but if it's heavy enough, it's almost same. So the best region is like this. And then maybe like another, this is a 1 sigma. Well, this is not very good. It's like this. And then it's like this. So this is 2 sigma. And the center is 1 sigma. And best fit is actually anywhere here. So this is the best fit. And then of course there are constraints. Like a most robust constraint is from the kink search of the sterile neutrino. So there is a beast measurement. And then there is an old beta decay measurement somewhere here. So this is energy scale of the aluminum. Okay. And then I also have to mention that there is a bound, because there are a bunch of Borexino talks. So Borexino do look for the sterile neutrino, looking for like this, maybe it's like this. So there is a bound in this mass range, and there is a way out. So this is a Borexino bound. But together with the cosmology, let me mention. So cosmology, especially this is a, okay, cosmology. Because this scenario is too predictive. Mass scale is fixed and mixing angle is fixed. So usually it's dead. And as you can imagine, what is dead is that if you don't do anything, it's very dangerous because it's a relativistic decoupling. So sterile neutrino decouples around 20 MeV, which means that when they decouple, it's relativistic. So the number density divided by entropy density is very, very large compared to the usual like freeze out. So this is dangerous, but if you introduce like some neutrino mediator, especially the sterile neutrino mediator, so you have additional decay like nu to 3 nu, or you can also consider this kind of variation. So which is safe to do so. And also, especially this gamma gamma make the cosmology issue much, much less. So this is a one prescription to solve two issues. And also there is a bound from the pi plus decaying to, or minus, I don't remember, to nu 4. So this is actually naively not dangerous because we don't use this measurement for the BUD BUD. But the story is very different if the sterile neutrino is massive, right? So usually like this kind of calculation without 4, assuming the neutrino is massless, then like this matrix element is suppressed by electron mass. But if the sterile neutrino is heavier than electron mass, this process is enhanced by the sterile neutrino mass. So this one is dangerous. And this one is actually most difficult one to solve. And I needed to introduce a dimension 6 operator to destructively interfere this process. So this is actually the most ugly part of this scenario. But other than that, I find a self-contained scenario. Okay, so let me just finish. So my takeaway is that the quark measurement is very precise, but still there is a room to test the neutrino sector. I particularly look at the Cabibbo-angle anomaly because this is very well measured. But I think that idea can be generalized to the RD anomaly and things like this, because that is also like a flavor changing charge current processes. All right, so let me finish here. Thank you.
Time for discussion.
I have a question. Maybe I can write just formula.
Yeah, sure.
Tell me where that's maybe here.
Okay.
So there is this process searching for a neutrinoless double beta decay.
Yes.
Yeah, where,
so yeah, this I forgot to mention.
Where
yes.
you have some nucleus not change charge, no? You meet a couple of electrons.
Yes.
No?
Yeah, I know. Yeah.
Yeah. Then you have W.
Yeah.
Radiating
yeah.
electrons, couple of neutrinos. Now, this depends upon the mass.
So if you do that type 1 seesaw, it's dangerous.
Yeah,
yes.
I would say it's very dangerous
yes.
because.
But I didn't mention because there is a way out, which is.
Just right to explain how dangerous it is. This M beta beta, no, is say less than 0.1 electron volt, more or less. And the contribution you have here is something like theta E squared times M4.
If you use a type 1 seesaw,
yes. Which is 1 MeV times 10 to minus 3, so it's 10 to 3. Much
no, I understand. So I have to use, for that reason, thank you for asking that. So I have to use the inverse seesaw to avoid this issue. So basically, pseudo-Dirac neutrino. So this like a one. So as you can show, that usually like if you use a type 1 seesaw, if you fix a mass and mixing angle, predict M beta beta, right? So if you use an inverse seesaw, because it's a Dirac nature, you don't have this relationship. So you can actually make the mass heavy while the mixing angle is order of 10 to the minus 3.
So you want the Dirac neutrino, basically. You want the neutrino mass is the mass.
It's not the Dirac neutrino. It's a pseudo-Dirac. It's a pseudo-Dirac.
Yeah.
So in terms of this process, there is a suppression of the lepton number violation, which is like, let's say, I have a mu, or, so this is actually not, so mu is actually the lepton number violating parameter, but this mu is not responsible for the mass of the mu4. Yes.
So you introduce another sterile neutrino.
As a part of life, yes. So it's not one, So I have a partner of the sterile neutrino.
What about the implication of this second sterile neutrino on the whole construction?
So honestly, there are many dangerous cosmology and so on, right? So one can, even if I get around the neutrino-less double beta decay, naively dangerous one is like a cosmology requires a mediator. And then like a mediator effective interaction is not very small because, so for example, this 20 MeV decoupling is very dangerous. So what I would do is that make the decoupling temperature lower than MeV, so 1 MeV. In order to do that, I have to couple this sterile neutrino to the thermal bath as much as possible, which means that this effective interaction is not small.
What about the lifetime of this new fall? at the scale of the age of the universe,
Lifetime of which one?
of nu4,
Yes, lifetime of mu4 is actually
with respect to nu plus gamma.
right. So it's decaying in the time scale of the Borexino. So when they produce from the sun, it should decay before we get this sterile neutrino. This is a one-time scale. And then in the laboratory, I don't want them to decay immediately because let's say if I have a gamma-gamma signal.
Why gamma-gamma? Why not just one gamma?
I don't think, okay. I didn't consider the one gamma. I didn't consider the dipole operator. I consider more like a mediator couples to the FF. But yeah, maybe one gamma is possible.
No, just the charge current. I mean, you have nu4.
With charge current, this is not enough to solve the cosmology. So I need some mediator. And then the reason why I couples to the photon is because actually sterile neutrino doesn't talk to the standard model except for the photon. So it can decay to photons relatively quickly.
But through the mixing, it couples to the charge current.
Yes, it does couple to the charge current, but it's not enough strength to make the sterile neutrino in the thermal equilibrium from 20 MeV to the 1 MeV.
No, I'm not thinking about that. I'm thinking about detecting the photon.
Okay, yes.
I mean, if the lifetime is appropriate.
Yeah. So yes. So we have to make the lifetime is kind of intermediate. Yes, you're precisely right. So because if it's decaying inside the detector, it's not recognized as a neutrino signal, right? So yeah, that is absolutely right. Of course.
So can't you just make the neutrino heavier than few tenths of MeV to instead of adding the new mediator to go around this cosmology problem?
So the issue is this pion decay. So pion decay of E nu4 is proportional to this one. So as you increase the mass, this problem gets
That's the
worse.
only issue.
That is the only issue. So then what happens is that I have to add a dimension 6 operator that is involving like a sterile neutrino. It's like a E, N, and then U bar D or things like this. And then there is a lambda square. I have to decrease the scale of the lambda as you increase this M nu4 because this is actually very precisely measured. And we try to get around. So this is actually the 3 months of this project to get around this bound. So, and then another 3 months to get around this bound. So yeah, so that is an issue. So we want to, there is no reason other than that to be, so it can be anywhere it's fine except for that bound. Yeah.
Yes. What is the robustness on the measurement of delta CKM? I mean, the fact that we have really an anomaly of 1.5 plus minus 0.5 10 to the minus 3 is a robust result, or there are a lot of doubts that instead this is just
I'm doing
zero?
the new physics. I should say I start from that this is assuming the robust result, but if I cannot use the new physics, where I suspect is the nuclear beta decay. So because this is a very precise, like an error bar they reported is very small. It's a bit subjective, but so they have an inflated error bar from the let's say 2016 to 2020, but measurement didn't change much. So systematic uncertainties are added and so on. So but still there is a 3 sigma. So maybe if you have an extra uncertainty which is missed, then maybe this 3 sigma becomes 1.5 and so on. But important thing is that to check this one, there are neutron measurements, right? So neutron measurement and also pion decay measurement is also there, which is still not as good as nuclear beta decay. Neutron lifetime itself is a big topic because the two measurements are controversial. So, but let's say one of them is like a bottle one, which is more or less consistent with nuclear beta decay, but error bar is still larger than the nuclear beta decay. So this is one thing I come up other than new physics. And of course, another branch of the new physics activity is messed up the quark sector, right? But this is everybody else can do, so I try to do other way. But yes, this is another direction beyond the standard model.
Okay.
But per allowed beta decays are by far the best, huh?
It's not actually by far. So that's a
I
good
mean,
news. So it's a
from
factor
from
of two, factor
yeah,
of two-ish.
no,
So it's not by far.
No, what I mean is that the case that we can calculate the most precisely, super loud, 0 plus 0
Yes,
plus
super loud,
decays
0
are-
plus 0, yes.
Calculation are not that easy for what I remember. I mean, the calculation of since the measurements are so precise, they should include a number of corrections that are not that easy to be evaluated. And indeed, this was revised in the course of the time.
So maybe this anomaly itself may be an interesting challenge for nuclear physics, or this also like a form factor related things. Like maybe anomaly is gone after we understand standard model better, but it's an interesting exercise.
Okay.
Yep.
If there are no more questions or comments, let us thank the speaker again.
Thank you.